Continuing here with section 3.2, let's look at how to find the GCD of a few different values. So we want to use our Euclidean algorithm. So thinking of this as m and n, we want to use the idea that m is equal to some quotient times n plus a remainder, and then we're going to just keep repeating this process. So we're starting out with 1776. So we want to think about how many times can 1492 go into 1776. So this is one we can probably do in our head. So we have 1 times 1492, so our quotient is 1, plus we need a remainder. So to get the remainder, we want to take 1776 minus 1492. We end up with 284. So based on the theorem that we saw before and using the Euclidean algorithm, the idea is that the GCD of 1776 and 1492 is going to be equal to the GCD of 1492 and 284, slightly smaller numbers for us to work with. So I'm going to take this 1492 and bring it down. I now want to find the quotient for 1492 and 284. So if we come over to our calculator, 1492 divided by 284. We're interested in the quotient, so how many whole times does it go in? So the 5 is what is important for us. So what we want to say is that 1492 is equal to 5 times 284. And now we need the remainder. So we want to take 1492 and subtract 5 times 284 to see what's left for our remainder. So in this case, our remainder is going to be equal to 72. So what we have now is that the GCD of 1492 and 284 is equal to the GCD of 284 and 72. So just keep going. Bring down the 284. We need to find out how many times can 72 go into 284. So we take 284 and divide by 72. We want to know how many whole times it goes in. It can go in 3 whole times, and so that's going to be our quotient. So we're going to have 3 times 72, and then we need the remainder. So take 284 minus 3 times 72. It's going to give you a remainder of 68. Keep going until you get a remainder of 0. So bring down the 72. 68 goes in 1 time, so 1 times 68. 72 minus 68 is 4. So the GCD of 72 and 68 is equal to the GCD of 68 and 4. Bring down the 68. 4 divides evenly into 68. 4 can go in there 17 times, so 17 times 4 plus 0. So our clue to stop is when we get a remainder of 0. So the GCD of 68 and 4 is equal to the GCD of 4 and 0. The GCD of 4 and 0 is 4. Every number divides into 0, so the GCD will just be 4. So what this tells us is if we back up step by step by step, this is also going to be the GCD of 1776 and 1492 is also equal to 4. So this is the largest number that divides into both 1776 and divides into 1492. Let's try again. A little bit smaller numbers this time, 89 and 55. So we start with the 89 on one side. We'll start with our larger number each time. 55 can go into 89 1 time. So 1 times 55. If we subtract 89 minus 55 is equal to 34. So bring down the 55. How many times can 34 go into 55? Well, 1 time. If we subtract, our remainder is 21. Bring down the 34. 21 goes into 34 1 time with a remainder of 13. Keep going. Bring down the 21. 13 goes in 1 time with a remainder of 8. Bring down the 13. 8 goes in 1 time with a remainder of 5. Bring down the 8. 5 goes in 1 time with a remainder of 3. Move up here. Start with the 5. 3 goes in one time with a remainder of 2. Bring down the 3. 2 goes in one time with a remainder of 1. And finally 2. 1 goes in there 2 times 1 plus 0. The GCD of 1 and 0 is 1, which means the GCD of 89 and 55 is also equal to 1. When this happens, when the GCD is 1, we call these two numbers relatively prime. So anytime the GCD is equal to 1, we call these numbers relatively prime because they have essentially nothing in common that divides both of them except for 1, and 1 divides everything. So now we want to take this idea and look at what's called the extended Euclidean algorithm. So this starts out the same. The first step is to just find the GCD using the Euclidean algorithm. Then we're going to use this same process backwards to figure out a solution to this equation. M times x plus n times y is equal to the GCD. So we're going to find solutions for x and y that satisfy this. These solutions will not be unique. There are other solutions, but this gives us one solution to an equation that has two variables. So let's try it first here for 341 and 217. First, just find the GCD, just like we were doing on the last two examples. So 341, 217 goes in there one time. You take 341 minus 217, you get 124. Bring down the 217, 124 goes in once. 217 minus 124 leaves a remainder of 93. Bring down the 124. 93 goes in one time. 124 minus 93 leaves a remainder of 31. Bringing down the 93. 31 divides evenly in there. 3 times 31 is 93. The remainder of 0. So the first step is that we found that the GCD of 341 and 217 is equal to 31 because the GCD of 31 and 0 is 31. So the second part, so this is the extended part, is now we're going to work backwards. To find a solution to this equation, m times x, so for us it was 341 times x plus 217y is equal to 31. So usually when we want to solve an equation that has two variables, we have a system of equations, two equations with two variables. Here we only have one equation with two variables, but we're going to use what we already figured out. So since we want it to be equal to 31, I'm going to start out using this line that I had right here, and I'm just going to rearrange some things. So I'm going to take this line, bring it right up here. If I solved this for 31, I would have 31 equals 124 minus 1 times 93. So just taking that line from when we were working our Euclidean algorithm and rearranging some things to have the GCD of 31 on one side by itself. So now we're going to go backwards again. This 93, I want to look at that one. I'm going to use this part here to rewrite that I can rewrite 93 using these two terms, that 93 is equal to 217 minus 1 times 124. So I'm going to replace this 93 using this line of my Euclidean algorithm. So let's try that out. So I still have my 31 here. I still have my 124. And in place of the 93, I'm going to write 217 minus 1 times 124. Well, taking a look at what we have a couple different terms that have 124, so I'd like to combine those together. So I have 124. You take a negative 1 times a negative 1, you have plus another 1 times 124. So if I have 124 plus another, now I have 2 124s minus 1 217. Now, I want to take a look at this 124 and think about how we could rewrite that. Let's grab another color here. So I'm looking at this 124 here. Notice that there's a 124 as a term here. So I'm going to replace that 124 with this whole group of terms here. So we still have our 31. I'm going to take out that 124 and replace it with 341 minus 1 times 217. I still have my minus 1 times 217 at the end. So I have 31 equals 2 times 341. 2 times a negative 1, I have minus 2 217s minus another 1. So minus 2 and minus 1, I have minus 3 times 217. So notice that this is in the format that we were interested in the equation that we wanted to solve. This 2, the number times our 341, is going to be our x. This minus 3 is our y. So x is equal to 2 and y is equal to negative 3. Let's check this on our calculator that it really does seem to make sense and give us 31 as expected. That if you take 2 times 341 minus 3 times 217, it should give us our GCD of 31, and it does. So the solution to this equation is you can solve this equation we started with if x is equal to 2 and y is equal to negative 3. Let's pause here. We'll start in another video with another example of this extended Euclidean algorithm.